Okay, so in our last class, we're in section 13.6, and we learned about surface integrals in our last class, and we learned about how surface integrals are derived, and we talked about an example dealing with surface integrals and how to compute surface integrals. And surface integrals can help us find what's called a flux through a membrane. So, like for instance, you could have, let me think of an example here. Like you could have a surface and there's like heat flow across the surface. Okay, so that is a type of flux. That's a type of flux. Basically, you have a vector field that represents a flow, some type of flow. Okay, it could be an electric field flowing. It could be uh, sorry, I want to say it the right way. It could be heat flow, and it's going through a membrane. And you're interested in finding the net rate of flow. Okay, so that's what flux is, and surface integrals are helpful for computing flux. So let's talk a little bit about what an oriented surface is. So remember when you studied Green's theorem, remember Green's theorem? Green's theorem was a theorem that allowed you to compute the work that a force field does in moving a particle once around a closed path in the XY plane. Okay, and remember you had positive orientation, okay, and then there was negative orientation. So for Green's theorem, if you know the particle, when it moves around its closed path, if it moves around that closed path in a counterclockwise direction, is that positive orientation or negative orientation? Counterclockwise is that positive or negative orientation? Good, Ian. Good, Ellie. Positive orientation. Okay, so we can talk similarly about surfaces. Okay, so let me go down here. So you see here in figure 6, and let me see here, maybe I will highlight. Okay, so there we go. So if it's possible to choose a unit normal vector, n, at every point such that n varies continually over the surface, then we call the surface S an oriented surface. And the given choice of the vector n provides our surface with an orientation. Okay, and so think about, like, for instance, you could think about like a fishing net, fluid going through a fishing net. Fluid could come in the fishing net from the outside, or it could go through the fishing net from the inside. That's what those normal vectors are representing. Outward flow, normal vector, unit normal vector 1, or inward flow, unit normal vector 2. Okay, so the orientation is, as you see in figure 7. Okay, you have this outward orientation on the left, and you have this inward orientation. So again, a fluid or heat could be flowing in or out of the surface. And the one orientation gives you what's called positive orientation, the other gives you negative orientation. So in figure 8 here, positive orientation is when the unit vectors are outward from the surface. That's called positive orientation. Okay. Negative orientation are when your unit vectors flow inward from the surface. Okay, and all of these, the vectors, well, yeah, are now I want to say, if you have a vector field that's flowing, like let's take figure 8. Figure 8, you have it, let's say you have a vector field flowing that outward through the surface, okay? And you're looking at, you're trying to understand the net rate of flow with regards to positive orientation. Well, the vectors in the vector field aren't going to necessarily be parallel to these pink or purple unit normal vectors you see in the picture. But when we compute the flux, we're doing it relative to to how those unit normal vectors point, basically perpendicular to the surface. All right. Are there any questions so far? Is this for those that have seen flux? Is this agreeing with what you've seen? Okay. Thank you, Charles. All right. Very good. Very good. So okay. Now, how are we gonna construct? You know, how are we going to uh, compute surface integrals? Well, one thing that is, of course, interesting to note is that in like the, let's see, do I have, yeah, the normal unit vector, if you have a surface, if you have a surface that can be written as z is some function of x and y, then the unit normal vectors, you can find them using the formula you see there in figure 5. So what are they doing there? They're taking the normal vector with components negative partial of g with respect to x, negative partial of g with respect to y, and 1. And they're dividing, so that's the direction of the vector. And they're dividing that vector by its length. So you get a unit normal vector. Okay, so remember when you, let me just go back here. In 13.6, when they talked about graphs, so, you know, if you have a surface that can be written as a function of x and y, then the derivatives of the vectors of the two parameters x and y are given as you see highlighted in the box there, in the highlighted gray box. Those would be your derivative vectors. And of course, we know that for computing the surface integral, we want the cross product of those vectors. And the cross product of those vectors, I want to try to get this to show good, is equal to the vector with the first two components, you know, negative partial derivative of g with respect to x, negative partial derivative of g with respect to y, and 1. And so that cross product vector, which would give a vector perpendicular to the surface, okay, at the point x, y, z on the surface, that cross product vector, if we were to want it to be of length 1, then what we would have to do is we would have what you see here. Okay, so that's one way to get a unit normal vector. So the unit normal vectors are the, like when we do a positive or negative orientation, we're doing it with respect to these unit normal vectors that point outward or inward from the surface. Now, of course, another way to get a unit normal vector, right, is to just use the definition of what the unit normal vector would be. It would be the cross. So if you have a vector function R of two parameters u and v that scratches out a surface in space, the derivative vectors, the cross product of the derivative vectors generate vectors orthogonal perpendicular to the surface. But if you want those vectors to be unit length, you have to divide by the length of the cross product vector. Okay, so two ways to get these normal vectors. All right, but we're going to come up with a formula that allows us to compute the flux, and this formula 6 is actually going to be the key, one of the key formulas we'll use to help us derive that equation for flux. I like, again, whenever I do a problem, a surface integral problem, I always do it using the parameterization approach. I don't like to use the approach where find where the z is a graph, and then I get these formulas. I know the book does it, and sometimes like in the watch it videos they might do it, but the problem is that it doesn't always work. Like if you have a cylinder, that surface you have to use a formula like this. So okay, well let's continue here. So all right, so we get to the next page, and they talk about surface integrals of vector fields. Okay, and they have a lot of things they're talking about here. A lot of things they're talking about. So they say, all right, suppose S is a surface oriented, either it's positive or negative orientation with unit normal vector n, and imagine a fluid with density, some density, and some velocity field flowing through S. So the fluid behaves according to the velocity field or vector field, V, and the fluid has some density. And it says, think of S as an imaginary surface that doesn't impede fluid flow, like a fishing net across a stream. Well, then it says the rate of flow, mass per unit time per unit area, is equal to the density times the velocity. Okay, and they talk about taking the surface and dividing it up into small patches, and then we can approximate the mass of fluid per unit time crossing a patch as this interesting formula here, the dot product of the density times the vector velocity field with the normal vector times the area of the ijth patch. Okay, and there, there they have a little picture there, okay, of the surface and the ijth patch. So let's talk about this. This is really it's kind of abstract now what they're saying, right? It certainly seems. Hold on, I don't know what that's there for. It certainly seems like it could be a little bit of abstract, but look, we can make it very comfortable for us. So first thing I want to focus on is, okay, when they say, hold on here. Okay, so they say the rate of flow, okay, so the velocity vector field gives the vectors, it gives you the direction of the flow, and you're multiplying those, hold on. You're multiplying that velocity field by the density. And they're saying that the units are mass per unit area per unit time, per unit area. Okay, so let's talk about that. I want to talk about that. Let me go to the whiteboard. All right. And one moment. let's see, I've got to find my stylus. Here it is. Okay, so density times a velocity field. Okay, now density. Okay, let's just suppose that density, the units are grams per cubic feet, right? So how many remember that density is equal to mass divided by volume? I'm sure you remember that. Give me a thumbs up if you remember that. All right, Ian knows that. Yeah, density is mass divided by volume. So in terms of units, and Gordon knows that too, absolutely. In terms of units, density, the density here, I mean rho is your density, right? So density can be thought of, for instance, as, say, grams per cubic feet. I'm just giving an example here. And now we have this vector v, which is velocity. So velocity, what would the units be for velocity? Well, what would, okay, Ian says meters per second, or we could say feet per second. Feet per second. Okay, so that could be like units for velocity. So, it's going to differ, but I'm just thinking of a very simple example here. Now, what we can do is we can write this as, maybe I'll make this SCC. We could write this as grams per second. Okay, and then in turn, the feet, well, the feet, we could have grams per second times 1 over a square foot. And we could write that as grams per second. Let me try to make that look good. One moment. We could write that as grams per second, all divided by feet squared. Okay, which is like feet squared over 1, right? But are we in agreement that in terms of unit analysis, grams per second times 1 over a foot squared is the same as grams per second over a foot squared? Are we in agreement on that? Give me a thumbs up if you're good with that. All right, Yunu's good. Ellie's good. Excellent. Excellent. And Madeline's good. Wonderful. Well, okay. Well, look at what we have here then. The grams per second is, I want to say this the right way here. That's mass per unit time. Mass per unit time. So this is a flow rate. This is a flow rate, or rate of flow. And then feet squared, that's unit area. So when you take the density and multiply it by the velocity field, you're going to get some number, right? But what are the units on that number? The units are flow rate per unit area. Flow rate, or rate of flow per, I want to be careful here. Now, hold on. Yeah, rate of flow per unit area. Are we good with that? Are there any questions on that? I'm going to go back to the book here, but I want to make sure you're comfortable with that. Give me a thumbs up if you're okay. Okay, Gordon's good, Ian. Well, I'm not, Ian, I'm not, thank you, Ellie, thank you, Charles. I mean, all I'm saying is the units for when I take the density times this velocity vector, the units are going to be, I can write the units. I mean, originally, like for this little example, the units were grams per second times 1 over the square foot. But I can rewrite that unit so that I have grams per second per feet squared. So it's flow rate per unit area, or rate of flow per unit area. And you see this then, if I go back to the book, here, this gets me then to, now I'm comfortable with what they're saying here. Now I'm comfortable that the density rho times the vector field v is rate of flow per unit area. Let's see, Charles. Yeah, I'm just keeping it simple. I'm just keeping it simple. So maybe my units are maybe I need to do a conversion, okay, for my units to sort of work together, but I'm just trying to keep it very simple, okay, very simple. Are there any questions? My units are good for imperial measurements. Okay, I'll stick with that. Thank you, Charles. Thank you. Thank you. Okay, Ian, you're good? Okay, all right. All right, well now let's see what's going on here. Let's see what's going on. So now if we continue, okay, they have a picture here in figure 10 of a surface. And there's that normal unit vector pointing perpendicular to the surface. And then there's the vector field F. Okay, thank you, Charles. Thank you. I'll make a note of that. Thank you. And there in figure 10, so you see the vector field, the flow of the fluid isn't coming out from the surface in a perpendicular direction. It doesn't have to. It can come out at like at an angled direction. But what we care about when we compute the flux or the rate of flow, the net rate of flow, is what part of the vector field, what contribution of the vector field is going perpendicular to the surface. Okay, what contribution of the velocity is going perpendicular to the surface in the direction of the normal vector. Okay, so what they say is, okay, and let's see, maybe I'll highlight. Now they're saying we can approximate the mass of fluid per unit time, that's a rate, crossing the patch on the surface in the direction of the normal vector by this quantity. Okay, so it's the dot product of your density with the times the velocity field with the unit normal vector times the area of the ijth patch. So let's see if this makes sense. Now notice it says in the direction of the normal, Okay, so let's go back to the whiteboard and let's refresh ourselves on something here. Way back in chapter 9, when you learned about the dot product, okay, you had some distance d vector and some force vector. Now, how do we find the work? How do we find the work that the force does in moving an object along the distance vector. The dot product, that's right, Ellie. It's the force, good, it's the force dotted with the distance vector. So that is equivalent to the magnitude of the force, or the length of the force vector, times the length of the distance vector, times the cosine of the angle in between them. Okay, this angle theta. Well, we're going to do the same thing here. We're going to do the same kind of thing for section 13.6. Okay, we can have, let me just see here, we can have like a normal vector, and then we have our vector field. So here's our vector field F. It equals density times the velocity vector. Here's the unit normal vector. Here's an angle in between. So if we want to know the contribution of the what, you know, the, let's say this the right way. Hold on here. One moment. If we want the rate of flow in the direction of the normal vector, then just like we did up here, we have to take the dot product of our vector field with the normal vector. Now, by the way, so is that okay? Is that okay what I'm saying here? If I want the rate of flow in the direction of the normal vector, I need to take the dot product of the two vectors. Just like we took the dot product above of the force vector and the direction vector, or the distance vector. Give me a thumbs up if you're okay with that. All right, Ellie, very good. Very good. Very good, Ian. See, we need a standard which to compute the flux. Thank you, Madeline. Thank you, Emma. And the standard is, what's the rate of flow in the direction of the normal vector? The vector field F here, the flow's coming out in a different direction. But what's the flow? What contribution of that flow goes in the direction of the normal vector? Now, in terms of units, let's remember our units here. So the density times the velocity vector, okay, that, as you recall, was grams. Hold on here. Let me see here. This was grams over second times 1 foot squared. Oh, now actually, hold on. What I'm going to do a little bit more here. Hold on, this is great. Let me do a little bit more here. I'm going to also now multiply this quantity, okay, which is simply the rate of flow in the direction of the normal vector. I'm going to multiply that by this area of the ith patch. Now, the area of the ith patch, for instance, okay, if we times that, that would be like feet squared. Well, what's going to happen to the feet squareds? what's going to happen in terms of, so this is a little like chemistry. How many remember in chemistry, checking your units to make sure that you're doing the right thing? How many recall that? You know, to make sure it helps support like what the work you're doing. Okay, Charles remembers it though. All right, same kind of thing. What's going to happen to the square feet here? What's going to happen to those square feet? When you take the dot product times the area of the patch, the square feet simplify out. Good. And what are you left with? You're left with this, grams per second, grams per second. And so that is mass per unit time. This is rate of flow. Okay, this is mass per unit of time. So, but it's going to give the flow rate of the velocity field. Okay, it's going to give the flow rate of the velocity field where the liquid has that density rho in the direction of the normal vector. Okay, it's going to give that rate of flow through the ijth patch. So in other words, if you want to find the flow rate, you have this fluid. In this case, let's say it's flowing outward from the surface, but it can be flowing inward too. But let's say you have this flow rate, you have this fluid. The rate of flow of the fluid with that density in the direction of the normal vector can be found by taking the dot product of rho times the vector field with the normal vector and multiplying it by the area of the ijth patch. And that's how that works. Now, if you wanted to find, by the way, if you wanted to find the net rate of flow across the entire surface, okay, if you wanted to find, I'll write that here, if you wanted to find the net rate of flow across entire surface, S, what would you have to do? What would you have to do? Well, you'd have to sample points all along the surface, and at every point, compute the dot product. Now the velocity, velocity is a function of x, y, and z, right? It's a function of x, y, and z. So to get the net rate of flow, across the entire surface S, you would have to add up. You'd have to sample points all along the surface, compute the dot product at each point along that surface, and then multiply it by the area of the ijth patch. Sorry. You have to multiply it by the area of the ijth patch. At that point on the surface. Okay. What's this going to turn into? This sum as we take more and more points on the surface. What's this sum going to turn into? Trying to make it look nice here. What kind of, well, whenever you, it's going to turn into an integral. That's right, Ellie. And what kind of integral? What kind of integral? Being the fact that we have this here, the area of the ijth patch. That's right, Ellie. It's going to be a surface integral. It's going to be a surface integral. Now, oh, there's another thing that I got to mention. I need two sums here, don't I? I need two sums, not just one. I need two sums, a double sum, right? Because if I'm, moving along the surface, I have to be able to move, X and Y have to be able to vary. Okay, so we'll go back to the book, but are there any questions on what, I mean, who's feeling reasonably comfortable with what you're seeing here? It's a little bit, I know, it's a little bit, it's new, but I'm trying to make it understandable. I'm trying to make it so that, you can appreciate what they're saying in the book. Is this helping? Maybe give me a thumbs up if this is helping. Okay, thank you, Ian. Thank you, Ellie. Thank you, Emma. Excellent. Okay, well, so now this net rate of flow is going to turn into a surface integral. Okay, and that would be your surface integral. See there? Density times velocity dotted with the vector n, and then d sub ds, d capital S, because the double Riemann sum turns into a double integral. Now, if we think of the density times the velocity as your vector field F, which they do here in that we started off thinking that in figure 10. Okay, there's the ijth patch and the normal vector and the vector field, ijth patch on the surface. If you think of the vector field as equal to density times velocity field, then equation 7 would become this equation here, or this double integral. And that's commonly known as that's called a flux integral. They mention a surface integral, put that in pink. A surface integral of this form occurs frequently in physics and is called the surface integral of flux, or flux integral of the vector field over the surface. And so now you know what this flux means. You know what this flux means. We don't want this to be an abstract concept. We want this to be a concept that we're comfortable with. And now we know what it means. And here then is the notation for your flux. So when they have the double integral across the surface S of the dot product of the F vector field and the n ds, that's surface integral. that we denote as the double integral of S of f dot ds vector. That's called flux. So whenever you see that, you think of flux. But remember, the flux is a surface integral, right? The flux is, to compute the flux, you're finding a surface integral. Now, right now, the formula we have for the surface integral is on the right there. Let's see if we can simplify things a little bit. Let's see if we can find a way to compute the surface integral. And what we can do here, let me just highlight this. So they mention here, in other words, definition 8 says that the surface integral of a vector field over S is equal to the well, I don't want to get too technical here, but what we need a simpler way to find our surface integral. So what we're going to do is we're going to take the normal vector and we're going to replace it by the cross product of the derivatives of the parameter vector, or the vector of two parameters with respect to u and v, and then we're going to divide that by its length. So we get a normal unit vector. In other words, what I'm saying is that the normal unit vector is equal to the cross product of those two derivative vectors divided by the length of that cross product vector. The normal vector, the length of that normal vector is going to equal 1, right? Because you're standardizing. You're dividing a vector by its length. So what they do back here then is they replace the normal vector, okay, in that formula above with the cross product vector divided by its length. But then you have this, they replace the ds also with the cross product of ru, rv, dA. Now what's that about? Let's talk about that. So the ds, okay, so, you know, again, you have some patch here, right? You have some patch, and you have these cross product, you have these vectors, RU, RV. But we learn that if we want to approximate the area of the patch, we really got to approximate the area of just the very corner of the patch. That's okay, it's still a patch, right? And so what you do is the area, the delta S area, is just equal to the cross product of delta U. Let me do it the right way. You're right. Delta U times the derivative vector R sub U with delta V times the derivative vector R sub V. Okay, that's that area of a parallelogram, right? So these little vectors here, I'm sorry, I'm just trying to draw it the best I can. Okay, those little vectors are these vectors. And you can bring out the delta U and the delta V, and the delta U times delta V is just like delta A. Okay, it's like a base times a height. So that means then that ds is approximately equal to the cross product of R sub U and R sub V dA. Okay, are there any questions on that? Well, and now what we do is we go back to the formula. Let me see, one moment. So I think I wrote that okay. One moment, let me go back to the book here. So now you see down here, do you see how they replaced the ds with the cross product dA? Maybe give me a thumbs up if you see that in the highlighted box. That's what I wrote, and thank you, Ian. And that's, class, that's what I wrote in the whiteboard. Thank you, Ian. Thank you, Ellie. That ds, D, capital S, big S stands for surface area. Capital DS is approximately the cross product times dA. Good. All right, and then what's going to happen? You're going to get some simplification here. Thank you, Madeline. And so now, here we go. You have a way to compute the flux. Now you have a formula to compute the flux. So there you go. And so computing the flux is equivalent to computing a surface integral. Okay. Are there any questions on that? Okay, I'll tell you what, let's try a problem out here. Let's try a problem out. Let me find it here. Okay, let me give you a moment to copy this example down, okay? Okay, so let's look at this problem. We want to find the flux of this vector field across a closed surface formed by the paraboloid given by y equals x squared plus z squared, where y is between 0 and 1, and a disk. Okay, so you have a paraboloid like a bowl. Okay, you have a paraboloid like this is a bowl. Does the bowl open up and down or sideways? Based on this equation, y equals x squared plus z squared. Good, it opens sideways. That's rightian. What axis does it open along? The positive axis or well, what axis does it open along? The positive x-axis or the positive y-axis? Good, positive y-axis, good. And then there's a disk. There's a disk. Okay, and notice the disk, you need two equations to describe this disk. The disk is the points x squared plus z squared less than or equal to 1. But then you let y equals 1. And we're assuming outward is positive orientation. Now what we want to do is, let's draw a little picture. We're going to draw a little picture of this paraboloid. It's just a sketch. And keep in mind, when they say compute flux, that means you're going to be computing a surface integral. And in this case, because you have here a closed surface S, well, there are two surfaces, right? There's the paraboloid, and then there's the disk itself that stops the paraboloid. So it's a closed surface. So you're going to need to find flux through both through two surfaces. Now, again, whenever I do a flux problem, since the flux problem is a surface integral problem, I like to use the parameterization approach towards finding the flux. So that means I'm going to find the parameterization of the paraboloid and compute the flux along through that surface. And then I'm going to find the parameterization for the disk and then find the flux through that surface. So here we go. All right, here's a picture. Let me give you a moment to copy the picture down. And the flux is computed with respect to positive orientation. If the surface were oriented negatively and we computed the flux, what would we have to do to the value of the flux if the surface had like a negative orientation and we computed flux? What would we have to do to the value? Multiply by -1. That's right, Ellie. Charles, that means moves inward, right. Negative orientation is inward. Yes, that's correct. So keep in mind now, you have this surface. The surface S is the union of surface S1 given here and surface S2 given here. S1 is the paraboloid, S2 is that disk. There's a vector field that is acting in this three-dimensional space. Think of it like a velocity field. And vectors are flowing through the surface. The question is the overall rate of flow at which those vectors are flowing, are overall the vectors in the vector field flowing outward from the surface or inward from the surface? And then, of course, what's the rate? Okay, so, all right, well, here we go. So the paraboloid, remember, is, what was the equation of the paraboloid? The paraboloid had equation y equals x squared plus z squared. So it makes sense that y would equal x squared plus z squared, and then my free parameters would be x and z. And then I have a little side question here that I'm going to answer in a moment. But let's try to get the cross product of the derivative vectors. So the derivative vector r cross x has components 1, 2x, and 0. And the derivative vector r sub z, has components 0, 2z, and 1. And I'm going to take the cross product of those two derivative vectors. Okay. And the order in which I do the cross product matters. I'm going to do, in this case, the derivative vector r sub x cross r sub z. And that's going to get me 2xi minus 1j plus 2zk. This is going to ensure outward orientation. Why? Well, we'll talk about that. Let me give you a moment to copy this information down, okay? And then we'll talk. Please let me know if you have any questions. All right, so there are really two, we go through the computations, and that's fine. And there's two sort of key questions here I want to ask before we move forward. Here's the first question, and here's the second question right here. So my first question is, I did the cross product in the order of r sub x cross r sub z. And that ensured outward orientation. So I get the vector 2xi minus 1j plus 2zk. Okay, that's my cross product field, vector field. And I'm saying that this will ensure outward orientation as opposed to doing the cross product in a different order. So if we look at the surface S1, if we look at the paraboloid, and we look at these normal vectors here, okay, they are going in the positive direction, right? They're going in the outward, they have outward or positive orientation. And I know that the R sub x cross R sub z is also going to give me vectors that go outward from the surface. How do I know that looking at the components? Which of these three components is telling me that this order for the cross product is correct? Is it the 2x, the -1, or the 2z? Well, let's go back to the surface, the paraboloid, surface S1. Let's go back to that. And let's just look at one of these, vectors going outward. Okay, we can look at either one. Let's look at this normal vector here, down here below. It has an x, y, and z component, right? And those components are either positive or negative, depending on what octant you're in. But let's be a little careful. This surface is in all 4 octants to the right of the xc plane. But the normal unit vectors, if you think in terms of components, x, y, and z, x could be plus or minus, y could be plus or minus, z could be plus or minus, depending on what octant, depending on what octant the point that your normal vector is protruding from. The normal vector protrudes from a point on the surface, and depending on where that point is on the surface, which would be in one of the 4 octants to the right of the xc plane, the components of x, y, and z for the normal vector, right, are going to be either plus or minus, right? Plus or minus. And I'm saying one of these 3 components, we're going to know for sure what one of these 3 components, the x, the y, or the z, we're not going to have a choice. It's always going to be one or the other. And I'm asking you which one. Based on these normal vectors. The normal vectors can go up, they can go down, they can go forward, they can go backward. Can they go both left and right? The normal vectors protruding from the surface S1. No, that's right, Charles. That's right. They are going to the left. So in other words, the normal vectors, no matter where they are on surface S1, the y component is going to be negative. The y component is going to be negative. I mean, because the vectors, yes, they can point upward, they can point downward, they can be moving in the forward in the x direction, backward in the negative x direction, but they're always pointing a little bit or a lot to the left in the negative y direction. And that means then, the normal vectors, I want to be careful here. The cross product vectors, r sub x cross r sub z, always have a component, a j component that is negative. So that means those vectors, I want to say this the right way, those vectors have to be coming outward from the surface, because if the vectors were like going inward, if those vectors, let's say the vectors, I want to say this the right way, let's say those vectors were going inward. No, let's say those vectors were going inward from the surface. What would the y component be for vectors going inward from the surface? What would the y components have to be? Would they be positive or negative? Those two red vectors I drew are going inward. Are their y components positive or negative? They're positive. That's right, Ellie. So, and it doesn't matter where I draw them on the surface. So that means that vectors flowing outward from the surface in the positive direction have to have y components that are negative. Well, our y component turned out to be a constant, turned out to be -1, but nevertheless, that tells me we have outward orientation, that this is correct. And also, I guess we answered the second question. Well, actually, hold on. Look at the vector field F. The vector field F is yj minus zk. So do the vectors in my vector field flow inward or outward from the surface S1? Well, the surface S1, let me write down that vector field again. Vector field F of x, y, and z is equal to yj minus zk, right? You write it a little more nicely. Hold on. I'll put it in blue. Oh, come on now. Get me off that, please. Thank you. I like things to be neat. Okay, now, any point on the surface, there's a vector that goes with that point based on this vector field. Would the vectors be flowing inward or outward from the surface S1? The vectors in the vector field, the vectors generated from this vector field on the surface, okay, would they be flowing inward or outward of surface S1, that paraboloid? Look at your components. Look at your components. In particular, focus on the J component. It equals Y. That's writing inwards. Because the entire paraboloid, all the coordinates on the paraboloid have positive Y components. So the vectors are going to have to be flowing, you know, to the right. Now, maybe to the right a little bit, you know, but they got to be flowing to the right. So what's that going to tell you? What's that going to tell you about the flux across the first surface, S1, across the paraboloid? Would the flux be positive or negative with respect to outward orientation? So let's think about this again. Flux measures, so we haven't computed the flux yet, but I just want you to think about this in practical, sort of in simple terms. The flux rate is the rate of flow of the vector field through the surface, and in this case, we're talking the paraboloid. It's the rate of flow with respect to outward orientation. Okay. But, well, actually, hold on. We can do better than that, class. What about this K component here, the minus Z? The minus Z. If I were to, let me see here. I'm going to write this again. I mean, this is so important. We have to talk about it. You know, I don't want you walking away not knowing what this means. Okay, here's the vector field again. Okay, now across my surface S1, the paraboloid, we established that the Y, or the J component has to be positive. Has to be positive. What about the K component, negative Z? No matter where the point is on the surface, no matter where the point is on the surface, well, I'm not saying this the way I want to say it. I'm sorry, class. Let me rephrase it. Every time I think of a better way of how to explain it. Okay. Let me do this one more time here. We're almost there. Okay. So if you pick a point here, okay, if you pick a point on the surface S1 right here, and look at a vector from the vector field at that point, okay, I'm going to give you two choices. I'm going to give you two choices. Okay, two choices. I'll just try to, I'm going to draw a big vector so you can see it. So you can see it. Okay, is that vector, okay, right here, based on the vector field F, is that vector going to be pointing in the orange vector direction, let's say, choice 1, or is it going to be pointing in the purple direction vector, choice 2? What's going to be the right choice? Choice 1, good, the orange. Because up there, the y component is negative. So the vector has to be pointing to the left. And then the z component is positive for this red point. You know, it's above the xy plane, and so it has to be pointing downward. So, okay, so the vector field, that at that point, the vector in the field is not going outside, it's not going outside of the surface. It's pointing inward to the surface. And the same thing here, if you pick a point down here, below the xy plane, there the z is negative, that vector is going to have to be going like in this direction as well, because the y component is positive and the and the negative z, which points, you know, in the k direction, that's going to be positive because z is negative. So this field, all the points on the surface are flowing, the vector field from on all the points of the surface is flowing inward to the surface. So with respect to outward orientation, positive orientation, would the flux rate across surface S1 for this vector field be positive or negative? Would it be positive or negative? It would be negative. That's right, Ellie. It's just like, remember the problems you had with work. Okay, if you have a particle moving in space, and the vector field's acting against the particle overall along that particle's path, is the work positive or negative? The work would be, if you have a particle moving in space in some vector field, and you want to compute the work that the field does in moving the particle from an initial point to a terminal point, and overall the field is acting against the particle's movement, then the work that the field does in helping the particle go from the initial point to the terminal point, would that work be positive or negative? It would be negative. Good, Ellie, good, Ian. It's the same kind of thing here. The flow of the vector field, the direction of the vectors in the field on the surface are going inward to the surface. They're not going outward. So it goes, it's not inward orientation. The flow of the field is inward instead of outward overall. And so the flow rate, the net rate of flow should be a negative value. And on that note, then, let's continue on. So now we want to get the flux. We have our cross product here. So you'll want to listen to these recordings. Is this, let me just ask, Charles, I know you had some flux. Is this sort of jiving, agreeing with your intuition on it? Okay, good. So, you know, good. So, great. All right, well, let's continue. Let's get this flux. So the flux across surface S1, here's and Charles is saying flux of a magnetic field across a gantry. Okay, and you know, I'm sure some of you have more experience than I do in seeing applications. You know, I just want you to feel comfortable with the math, and then But yes, thank you. Electric fields. So okay, here we go. So here is the flux across surface S1. That's this double integral, okay, of the dot product of the vector field with the cross product of the derivative vectors. That's formula 9 in section 13.6. We remember that the vector field is a function of position, and position is given by the vector of the two parameters. The tip of that vector traces out the points on the surface. Well, the vector field of the two parameters, the vector field R of x and z, is given by components x squared plus z squared, and z. So the fact that your vector field is yj minus ck means that the vector field evaluated at the points along the surface has components 0, x squared plus z squared, and minus z. Let me stop there for a moment. I want to make sure you're good down to this step. Okay, are there any questions down to here? Please let me know. I made these two little notes on the side to help you just to help you, these little notes here, to help you see the transition from here to here. You have to let me know if you're uncomfortable, okay? Okay, and then we do the dot product. And if we take the, if we consider our parameterization for surface S1, okay, for surface S1, I mean, let me just go back here, class, and put something in here. Hold on. I want to add something to your notes here. The x squared plus z squared is less than or equal to 1. When you do your parameterization, you need to state what the limits are on the parameters. Well, the x squared plus z squared is less than or equal to 1 gives you the limit on the parameters. It's a condition. And that's because the entire surface, any point on the surface, the x and y components at that point have to satisfy that x squared plus c squared is less than or equal to 1. Okay, and so that being said, that then tells us that the region D is going to be a circle of radius 1. So I know that I'm going to be using polar coordinates to compute this double integral. Now I didn't compute it all. I didn't like go all the way with it, but you could work it out, and you'll get negative pi if you work it out. In this case, x squared plus c squared is equal to r squared. And, you know, here, x is r cosine theta, and z is r sine theta. And so indeed, our flux was negative across that first surface. That made sense. That made sense. Please let me know if you have any questions. And give me a thumbs up when you're done copying, and then we'll then look at the flux across the second surface. Okay, Ellie's good, Madeline's good. Ian's good, Charles is good, all right. Gordon, how are you? You're good, all right. Emma, how about you? Very good, Gordon. Good, all right. Let's go back to our picture here. Let's go back to our picture. And here we are again. Now we're on this second surface, this disk. Here's the vector field. Do you think the flux across disk, this second surface, S sub 2, this disk here, do you think the net rate of flow would be positive or negative? Would the flux be positive or negative? It's going to be positive. No question about it. No question, because the vectors are moving to the vectors in the vector field are moving to the right. They're moving to the right because we're to the entire that solid is to the right of the xc plane, which means the y components are to the vectors are positive. And so flowing outward from that surface S sub 2. That's going with the flow in the sense, in terms of the positive orientation. Those vectors are going with the flow in terms of the normal vector positive orientation. Okay, so let us continue here. So here is then my second surface. There's the vector parameterization, or the vector, I want to say it the right way. Section 10.5 is when you learned about parametric surfaces. Yeah, the vector equation would be given, they call this the vector equation here. Well, the disk is at y equals 1. So y equals 1 is constant, and then x and z are free. And it can be shown that the cross product, now this time you're going to do the cross product of rz cross rx, because that gives you 1j. That ensures the outward orientation. Okay, that cross product has to ensure outward orientation. Now, if you ended up doing Rx cross Rz, you would just say, oh, okay, well, that's negative 1j. That means the outward orientation. You know, negative 1j is the negative orientation inward. I want positive orientation, so I'll just make it a positive 1j. You know, so that's the one thing you have to always check on, that you have outward orientation for your problem. And then you just compute the flux. And when you're ready, I'll go to the next page. Just let me know. Okay, Charles is good. Gordon's good. Madeline's good. Wonderful. Ellie's good. All right. Let's continue. Juliana's good. Excellent. Okay, so we do the dot product. The dot product here is going to equal 1 between those two vectors. And so, you know, here is our double integral. And again, now, let me just see here. One moment, class. I really don't want dr d theta. Let me fix that. Hold on. Or do I? Yeah, I do. I want to use polar coordinates. So yeah, that's fine. No, that's good. That's good. And I'm gonna get pi. So to get the whole flux across this surface, remember the surface S is equal to the union of the first surface, the paraboloid, and the second surface, that disk. So you just add the flux together, the two fluxes together, and the net rate of flow is 0. That happens sometimes. All that work and you get 0, right? But it's important. The book has some nice examples as well. This example I did is actually an additional example from your book examples so that you can get some variety. Sometimes students get a little bit, when they see like a surface that isn't an up and down type surface, but a sideways surface, it makes them a little nervous. And I don't want you to get nervous, on that. If you just stick to the fundamentals, you'll be okay. You'll be okay. Before we go on break, I'd like to show you one thing from the ebook. One thing here. Okay, give me a thumbs up if you're ready. Are there any questions on this one? Notice the notation, by the way, class. D sub S vector, that means flux. D sub S vector, that means flux. Okay, very good. Let's go to the book real quick here. Okay. So here is the flux formula. And naturally, you'll have access to this on the exam. Okay. again, you know, the book likes to talk about these special cases. So for instance, again, if you have the case where your surface can be written as a graph, z is a function of x and y, then the flux formula, okay, the cross product of Rx and Ry is given by that vector there with the partial derivatives there in it. The vector, the flux can then, in the special case where z is a function of x and y, you can compute the flux using that formula. Now, this would work, by the way, if x were a function of z and y, or y was a function of x and z, like in the example we just did. The work we did, in particular when we did our flux integral, if you were to use, like if you were to adapt, you'd have to come up with the formula for it, right? But if you were to treat x as z as a function of x and y, and then you could come up with a formula similar to what you see in Formula 10 there, and can compute the flux as well. That's okay. The reason I like to use the general formula that you see here is just because it always works. It always works. Okay. And note also, they say compare this equation 9, this flux formula, compare that to the similar expressions, for evaluating a line integral. Okay, so compare that with the line integral formula below, or line integral of a vector field. Isn't that, I mean, how many think that's absolutely cool? The line integral of a vector field involves a dot product. The flux integral involves a dot product. I mean, compare those two formulas. How many think that's sort of like so beautiful? It's really beautiful and amazing. The similarity there. I mean, they're different, but I mean, isn't math and nature kind of beautiful? Okay, thank you, Juliana. I got to end my recording with somebody saying yes. Might we have another person say yes too? Thank you, Juliana. Didn't have to. Who thinks so? This is pretty amazing. Okay, thank you, Charles. Excellent, excellent. It is. All right, let me stop the recording.